Okay, so that's a P series. Okay, and the theorem says that the P series, a P series, converges if P is more than 1, if the power is more than 1. Well, again, what this means is that the denominator, if P is more than 1, if the power is large enough, then the denominator gets large fast enough. So 1 over that denominator gets small fast enough. Therefore, the whole thing is convergent. And diverges if P is less or equal than 1. Okay, again, just like the P integral. Same thing. The proof of this requires the P integral theorem, basically, which we've already proved. Okay, so examples. 1 over, let's say, cube root of n. This is the same as the sum 1 over n to the 1/3, and this is what? Convergent or divergent?
Divergent.
Divergent. Yeah. Because P is equal to 1/3, and that is less than 1. Okay. Or 1 over n squared. This is convergent. Since P is equal to 2 and it's more than 1. Okay. Yeah. Again, guys, remember, we can only say if these series converge or diverge. If the series is convergent, most likely we can't find its value. That's, I've said this before. The only series whose value we can find are the geometric series and telescoping series. Okay, for the rest, we are not able to easily find their value. And I've mentioned this before, the value of this series actually using some advanced math, it's pi squared over 6. How they get that pi squared over 6? Again, it's got nothing to do with integrals. So again, if you want to show whether this converges or diverges using the integral test, the integral from 1 to infinity of 1 over x squared dx, its value is not the same as the series. Okay, the integral just says if the series is convergent or divergent. It doesn't tell you what the value is. Okay, remember that series is a series gives you the sum of the area of these rectangles. Okay, and the integral gives you the actual area under that curve. Okay, so sum and an integral don't have the same value. Just please keep that in mind. All right. Okay, so going back to this series here that we answered yesterday, and we said this diverges. And this is important. So I kind of did go over the analysis of this series with you guys, but I want you to, again, I want you to listen and take this seriously. I want you to understand this. The book doesn't discuss any of it, okay? They don't. They just say, hey, the series converges, we're done, or diverges, they're done. They don't take the time to describe what's going on exactly, okay? But we did an integral test on this thing, and we said it's divergent, okay? Now, if someone knows the P-series theorem in advance, they might look at that and say, okay, here we have in the denominator n ln n. Without this ln n, you have the harmonic series and it's divergent. Now, with that ln n, with that extra factor in the denominator, you might say that the denominator is now a bit more powerful. The denominator increases faster. The terms get small faster, probably, in comparison to 1 over n. But with that ln n, this thing still diverged, which tells you that ln n is so powerless that its power is almost 0. Putting that ln n didn't have any impact on the denominator. It didn't change the behavior. It's still divergent. All right. So again, P-series theorem says if the power is more than 1, meaning that if it's epsilon slightly more than 1, then the series is going to converge. Again, you might say this is the power of this denominator is now more than 1 because of that extra ln n, and it's still diverged. Ln n is the least powerful function. And I said that on day 2 or day 3, ln of n increases really, really, really slowly. So slow that it's almost powerless. Almost powerless. It's not perfectly powerless, it's almost powerless.
Professor, I have a really good question on that example. For that example, so can't you like split that into like 2 terms? Like let's say 1 over like the series of 1 over n times like the 1 over ln of n, and since C you have like and then you can use like the P theorem that we just learned and say like 1 over
Alright.
n is like
So hold on.
divergent.
Hold on. I usually let my students finish what they're saying, but I'm
Sorry.
not gonna let you. I'm not gonna let you. Let's just go back. Let's go back to the very, very first thing you said.
Uh-huh.
You remember what you said?
Yeah, I was just saying, so can you like split that into 2? So like let's say like can we say this as like this series of 1 over n?
Say exactly what you said, Ahmed. Say exactly what you said. Can we split it into
Did I said two series?
two terms?
2 terms or yeah.
Two terms or two series, same thing. No, we can't. These are factors. These are factors, okay? We can't. How are you gonna split that?
Like we can't say I'm looking at it as a way to like rewrite it like, oh, 1 over n, like so like the sigma of n equals 2 to infinity, like of 1 over n times sigma of n equals 2 to infinity
Okay,
times 1
so
over n.
you are saying the summation of a sequence an times a sequence bn is equal to the summation of a sub n times the summation of b sub n.
Can we do that? Yeah.
Well, let's see. Let's see. So what does this mean? Let's write this out. If I write this out, this is n going from 1 to infinity. That's a1 b1 plus a2 b2 plus a3 b3 and so on. Okay, If I write the right-hand side, if we rewrite the right-hand side, we have A1 plus A2 plus A3. Okay, so on. And then the second sum is B1 plus B2 plus B3 and so on. Okay. Are these equal?
No.
Okay. So we can't say that 1 over n ln n summation is summation 1 over n times summation 1 over ln n. We can't.
Okay.
Yeah, because if you were to expand this thing, if we expand this, you would have to do A1 times B1, and then you would have to do A1 times B2, A1 times B3, A1 times every one of those terms, and then A2 B1, A2 B2, A2 B3. Okay, you can just look at the, if you don't feel like analyzing the whole thing, just look at the sum of first two terms. Let's just look at the partial sum. Okay, and let's just say n goes from 1 to 2 over here. So again, the question is, are these equal? If you multiply this out again, guys, that would be A1 B1, A1 B2, A2 B1, A2 B2. It doesn't equal that. Okay, does that make sense? Yeah.
Yes, that makes sense. And then like two people in the chat kind of also clarify what I kind of meant.
What did you mean?
So like Alex said, like he said like, I thought you mean the summation 1 over n times 1 over ln of n.
Summation what?
1 over n times 1 over ln of n. That's what I thought.
Okay, so is this what you were thinking or no?
Yeah, I was thinking that too. And then I was also thinking what they were thinking as well.
Well, okay, so you have this summation. All right, so since you understood all of that, I'm just going to erase it.
Yeah.
Okay, very good. So now you're saying do 1 over n ln n as the summation of 1 over n times 1 over ln n?
Yes. And so, yeah, that's what I was.
Okay, so if I were to expand this, that's n beginning at 2, I get 1 over 2 times 1 over ln 2 plus 1 over 3 times 1 over ln 3 plus 1 over 4, 1 over ln 4. So how is this different than, how is that different than this? Like,
Oh, it isn't.
yeah, what does it, it doesn't help us at all. It's just that this is our sequence.
Okay. All right, cool. Thank you.
Yeah, no problem. Yeah, splitting the fraction. I mean, how's that gonna help? Yes, that,
Professor, kind of expanding on what Ahmad was saying. Since we know that 1 over n is divergent, couldn't we just rule out everything else? Be like, this is divergent because 1 over n is divergent.
So yeah, so the whole thing is divergent.
why? What about the ln n then?
Well, I was wondering if it even matters. Like if we
Why
have
not?
if we have a divergent,
Oh,
we have
okay,
a portion that's divergent. Yeah.
so you're saying, oh, you're saying since we have a divergent portion, then it's divergent?
I'm asking if that is.
Okay,
yeah.
so what if I were to do this? 1 over n squared. So this becomes 1 over n squared. I have a divergent portion. Is this divergent?
No,
Okay.
thank you.
Yeah, no problem, guys. Just if you have these questions that you have doubts with, just try to write down examples and see if it's going to work on what you're thinking. if what you think works on different examples, and it, most likely it doesn't. Yeah, the summation notation is a summation notation. It's not a multiplication. You're not multiplying the summation by. Yeah, so be careful, please. This is just your sequence. If this was, if this is something you could partial fraction, then partial fraction, but this is not a polynomial, so we can't partial fraction anything. Moving on to the next section, I think I spent 3 days on integral tests. Next section is on comparison. So we still want to know if a series converges or diverges. And the integral test, as I've said before, there's almost a 0% chance that the integral test is going to work, because we most likely can't find antiderivative. Again, the integral test, the theorem was designed to see if an integral converges or diverges using a series. We are using the integral test exactly the opposite of what it's meant to do, okay? That's because integrals are very difficult to calculate. So the next test is a comparison test. The name kind of explains itself. You compare the series to another series. That's basically the whole goal of comparison. If I have, so I know I have geometric series, right? We know about geometric series. We know so far the harmonic series. We know the P series. Okay, we know exactly what to say when we see a geometric series or a P series. All you have to do is look at the common ratio or look at the power P if it's a P series. Now, if you have a series, you could probably compare that series to a P series that you know of and tell what happens. Okay, so for example, here we know that this P series converges because, again, P is equal to 2. It's a power more than 1. And again, if you don't understand why, you can do the integral test on it. And the integral will be finite. I think the integral is 1. We did that a while back. All right. Question is, does this series converge? Or diverge? Okay. Well, to answer the question, you have 2 options. One option is to do the integral test. We can actually find the integral from 1 to infinity of 1 over x squared plus 1 because we know the antiderivative of 1 over x squared plus 1. It's tangent inverse of x. So the integral test, it's not bad, it is doable, but it's not the most efficient way to go, because I can compare the series to this P series. And the reason for it is because as n gets big, when n gets big, in the denominator, the dominant term is not 1, it's n squared. That 1 just drops out eventually and you get 1 over n squared in a long run. And that is convergent, okay? So what I'm doing here is I'm comparing this to that. there are two ways that you can compare the series in question to a series whose convergence you know. We can do a, what's called a basic comparison, or we can do a limit comparison. And basic comparison is what we are going to talk about first. Okay. So if I write down a few terms of 1 over n squared, we get what? 1 plus 1 over 2 squared, that's 4, plus 1 over 3 squared is 9, plus 1 over 4 squared, 16, and so on. And let's also write out a few terms of 1 over sum 1 over n squared plus 1 to see how these two series compare. So here, if I plug 1 in and begins at 1, I get 1/2. Plug 2 in, you get 2 squared, 4 plus 1, which is 5, plus 3 squared, 9 plus 1, 10, and next one will be 1 over 17, and so on. All right, so notice that every term of this series is smaller than every term of this series. 1/2 is smaller than 1. 1/5 is smaller than 1/4. 1/10 is smaller than 1 over 9, and so on. I can't do these. Let's just do it in a different color here. Let's go with green, and let's do this in blue. Yeah. So 1 over n squared, that is in green. All right, so we are talking about the sequence, not the sum. You write those. You know what I mean. Yeah, that's less than 1 over n squared plus 1.
Greater than.
It's greater than. Yeah, oh, I have it.
Yeah.
Thank you. I have this backwards. Yep. Yes. Okay, perfect. Yeah, 1 over n squared is 1 over n squared plus 1 is less than 1 over n squared. I didn't even have to write these out to show this, because this denominator is larger than this denominator. So when you do the reciprocal, 1 over n squared plus 1 is less than 1 over n squared. And this is true for all n, as you see. Okay, so if every blue term is less than every green term, guys, make sure you're listening, then there's the same holds true about their sum. Okay, so if I add all of these, the sum is going to be less than this sum. Less than the sum of 1 over n squared. All right. And what we know about this sum is that it is convergent. This is actually pi squared over 6. Don't ask me how or why, but it is that. It's convergent. It is equal to some finite value. This is equal to m. M is finite since convergent. Okay. which says something about the sum of those blue terms. Okay, this says that the sum of 1 over n squared plus 1 is less than m. Imagine m is 3.5. Imagine m is 3. If something is less than 3, then that thing has to be finite itself. Anything less than a finite number is got to be finite. And that's what basic comparison is all about. Okay, so that implies that the summation of 1 over n squared plus 1 is also finite. Therefore, it is convergent. Okay, so what we are doing here is we are comparing our series to a larger convergent series, because since this larger convergent series is finite, then our series has to be less than that finite number, therefore convergent. Jose says, good example, guys. Jose's questions are always great. This example would not work if we were working with negative 1 over n. Absolutely, Jose. And one of the requirements of the test, which I haven't written the theorem for yet, says that the series must be a positive term series, or it must be an eventually positive term series. Yeah. But you get the basic idea, right? Any series less than a finite value has got to be finite. Okay, so let's write down the theorem. This theorem has two parts, one part for convergence and one for divergence. And again, it's very intuitive theorem. And again, this requires that our series to be positive term series. Yeah, so let's say we have two series. One of them is a sub n, sum a sub n, and the other is sum b sub n. Let these be positive term or eventually positive term series. Meaning that they don't have to be always positive, they can, but they must be positive at some point forward. Okay, there are two parts to this theorem. Part one says that if the summation, the series of b sub n converges, okay, and terms of the first series a sub n are less than terms of the second series b sub n whose sequence is b sub n. Okay, if this is true, then the series of a sub n is also convergent. Exactly like what we saw with that example. Okay, so I'll write that in blue so you can associate. And I'll write b sub n in green. You should know why, right? I wrote this example that I hope you understood in general. Okay, but again, if this inequality is true, then the sum A sub n is less than or equal to the sum B sub n, and the summation of B sub n is finite. So imagine again, this is M. So the sum of A sub n, the series of A sub n, is also less than that finite value. Therefore, it has to be finite. Okay. So since this is pi squared over 6, that's pi squared over 6, then the value of this series is got to be a number less than pi squared over 6. I don't know exactly what it is, but it's less. Okay. I don't know how to find this. I know how to find this, how to show this is pi squared over 6. But this one, I don't know how to. I think there's a trick. I don't know of. But trying to explain why this is pi squared over 6, it requires section 11.9 or 11.10, at least that knowledge. All right, and then the second part of the problem. Oh, so as long as they're both negative, yeah. But it's just a matter of sign change. Okay, so 2 says that if this is the one for divergence, and it says that if the summation of B sub n, the sum B sub n, diverges, pay attention to the inequality, okay, and A sub n is larger than B sub n, then, so think about it now. So here we have the series of A sub n, sum, guys, please listen. The sum A sub n by that inequality is now larger than or equal to the sum of B sub n. So now imagine the series of B sub n is divergent. So this is equal to infinity. Then there's the series in question, the series of A sub n also should be divergent. It should also be infinity. Anything larger than infinity is infinity. Okay, so again, common sense, thinking about it. I know a lot of you understood, but I want you to still think about it, okay? Always think about it. Yeah. All right, so let's do examples. And then we have the limit comparison. We'll do that later. But when you answer a question using comparison, one of the comparison tests, I want you to do the work in 4 steps. Okay, there are steps for running a comparison test, and I will discuss those steps. Okay, so again, question here is to show if the series is convergent or divergent, and here we have the summation n going from 1 to infinity of 1 over 2 plus 5 to the n. Okay, and we're going to use comparison. Okay, so let's look at the series, guys, and try to, first of all, try to identify the series. If you can identify the series as a geometric series or a P series, then you're done. You just have to say whether ratio is less than 1, between -1 and 1, or if it's a P series, if P is more than 1 or less or equal to 1. Okay, this is none of those. This is not a P series. It's not a telescoping series for sure. And it is not a P series. It would be geometric. This thing would be a geometric series if we didn't have that too. 1/5 to the n, a common ratio would have been 1/5 if I didn't have that too. Okay, so this is not none of those. It is gonna compare to a geometric series in a little bit, but this is not a geometric series. Okay, second thing you wanna do, I'm not writing these down, so you need to just listen. Second thing you wanna do, you don't have to, but you wanna do this, is run the nth term test in your head. In your head. Because most likely the nth term test is just gonna be inconclusive. But sometimes it could tell you the series is divergent. Just check the nth term test in your head by taking the limit of the nth term. What does happen to the terms of the series as n gets big? Well, it goes to 0. Terms get smaller and smaller. Okay, because 5 to the n in the denominator gets big and bigger. A sub n goes to 0, so the nth term test is not conclusive. Okay, it would be conclusive if that thing went to anything but 0. In that case, it would be divergent. Okay, so here our a sub n is, 1/2 plus 5 to the n. This thing goes to 0, inconclusive. Next test would be the integral test, and hell no, we don't want to do integral test, guys, on this one. How are you gonna integrate 1/2 plus 5 to the x? This, I don't even know how to integrate that. I really don't. Like after doing math, taking 45 math classes, I wouldn't know how to integrate that. So we don't want to do integral tests. Avoid the integral test as much as you can, unless the question asks you to do an integral test. Just don't. So next is the basic comparison test or comparison test. By the way, I forgot to mention, this is called a basic comparison test. Okay, that's the name of this theorem. BCT, basic comparison test. Okay, so here are the steps for basic comparison. Step 1 is to guess. We want to guess if the series is convergent or divergent. You know why we have to guess? Because I need to know what kind of inequality to choose. Okay? If B sub n converges, then I want to choose a B sub n that is larger than my A sub n. Right, I need to guess to see which one is going to happen, convergent or divergent, so I can choose the right inequality. Okay, you'll see that in a second. So here we're going to guess if the series converges or diverges, and this sucks about the comparison test, basic comparison test, because we have to do that guessing. Okay, and the guessing part, trust me, is the easiest part. So just look at the series, guys, and ask yourself, as n gets big in the denominator, what is going to dominate? This is all about, comparison test is all about dominant terms. Okay, so in the denominator, what is going to dominate and what we should ignore? I'm
The
asking.
5 to the n power.
Yes, this is the dominant term. 2 to the 2 here doesn't do much. So ignore that. You end up with the summation of 1/5 to the n, and that is geometric. It's geometric with ratio with ratio 1/5, which is between -1 and 1. So we guess that convergence. Yeah. The series behaves like 1/5 to the n, which is a convergent geometric series. So we're gonna guess convergent. Okay. I wish this was it. I wish our guess proved it, but it doesn't. I need to run the actual test. But the good thing is that when we do the limit comparison test, the next comparison test, we go based off of the dominant terms. Okay, but this is what you want to do. All right. Second step is that since we guessed convergent, then I need to come up with a sequence so that our a sub n is smaller than that sequence. I want this inequality to be satisfied. Okay, so find a sequence b sub n that satisfies the proper inequality. Okay, so this means that we want to find a sequence, again, b sub n, such that our a sub n is less or equal than b sub n. This sounds kind of hard, but this is the easiest part probably. Okay, this is the easy part. So write down your a sub n. Just write it down. A sub n is 1/2 plus 5 to the n. Okay, just come up with a sequence that is larger than that. And so it turns out that if I ignore the 2 in the denominator, very easy. If I ignore the 2, the result would be 1/5 to the n, and this sequence is larger than our a sub n. Isn't it? This denominator is larger than this denominator, so the whole thing is smaller than. Okay, or you could look at it this way: 2 plus 5 to the n is more than 5 to the n, because the left-hand side is 2 more. So if you reciprocate, then the inequality becomes less. Okay, so this is what you're going to take your b sub n as. Okay, because we guessed convergent. So step 3. You're going to prove or determine if the summation of, or the series of B sub n converges or diverges. Okay, so here we're looking at the sum of B sub n, and that is the sum of the series of 1/5 to the n. And this is, again, this is our geometric series. It's geometric because the ratio is 1/5. You can think of that, if you don't see it, you can think of it as the summation of 1/5 to the power of n. Anytime you have a series whose terms are exponential, when the variable is in the exponent, like that, then you have a geometric series. Okay, and this is convergent again because the ratio is 1/5. It's a convergent geometric series with common ratio r equal to 1/5, satisfying absolute value of r less than 1. That's why it converges. Common ratio is between 0 and 1, and we are done. Okay, so last step is you writing down the conclusion. Okay, so since A sub n is less than B sub n, and the series of B sub n we said is convergent, then by basic comparison test, the series of A sub n is convergent. Converges by basic comparison test. Make sure you mention the name of the test you're using. Okay. The guessing part is the worst part of these. Typically, if you have a series, if you can't identify what that series is like, or if you can't identify the parent series, then the guessing part is kind of tough. All right, but let's do another example here. Yeah, and here has to begin at 2 because 1 makes the denominator 0. Okay, so here our A sub n is 1/n root n minus 1. Okay, everyone, please message me privately here so I know you're here. Everyone, I need you to message and tell me what you guessed. Do you guess this thing converges or do you guess it's divergent? I need everyone to just say something privately in the chat box. I want to make sure everyone is here. I guess this is my way of taking attendance today. So always, to answer this question, always try to ignore the non-dominant term in the denominator. Okay? Those who say convergent, ignore the non-dominant. The non-dominant is this one. As n grows, as n goes to infinity, this term is growing negative. You're doing -1. That doesn't do anything. Okay. If this thing is 1 billion, 1 billion -1, that -1 doesn't really decrease it. It's just you take away $1 from $1 billion, it's still huge. Okay, so without this -1, you have a 1/√n, and that is a p series with p equal to 1/2, less than 1. That would be divergent. Divergent is what we guess. Because the series behaves like (1/√n), which is that's a divergent p series. Okay. Again, guys, with the limit comparison that we're gonna learn next time, with that limit comparison, we're gonna prove that the series behaves like, therefore it is divergent. It's a lot easier. The limit comparison is a lot easier. We'll do that on Monday, I guess. Okay, so second step, I need to come up with the proper sequence b sub n. Okay, so let's go back to the statement of the theorem. We guess divergent. That's what our guess is, divergent. So I need to come up with the sequence b sub n that is smaller than our sequence a sub n, and show that the sum of b sub n is divergent. Okay, so since we guess divergent, look at that and try to prove that. So here we need a sequence b sub n such that our sequence a sub n is larger or equal than b sub n. Okay, so what you do is write a sub n down. Okay, and again, don't think too much. Don't think too hard. Just see what would happen if you didn't have that -1. How does this compare? Can I compare this to 1/√n? 1/√n is this more or is it less?
Less.
It is less. Yeah. This denominator, so again, look, √n -1. Okay, this is less than square root of n. Obvious, right? Because the left-hand side is just 1 less. Okay, so if I reciprocate these 1/√n -1, it's going to be greater than 1/√n. Reciprocating will switch the direction of that inequality. Okay, so this blue sequence is greater than 1/√n, and that becomes your b sub n, thankfully. Okay. So typically with the problems in the book, the sequence that you're comparing your sequence with is typically a very simple p series or a very simple geometric sequence, p sequence or geometric sequence. Okay. Yeah, so step 3, just tell what happens to the summation of b sub n. It's the sum of 1/√n. Okay, that is sum, be as detailed as you can be. That's the same as 1/n to the power of 1/2. is divergent. And again, be more detailed, is a divergent p-series. Mention it's a p-series with p equal to 1/2. So you're saying why? Because p is equal to 1/2 and that is less than 1. You're not proving, guys, you don't need to prove that the p-series is divergent. We already know the theorem for p-series. The theorem says, and we are using that theorem. Theorem says if p is less than 1, then the p-series is divergent. You don't need to do integral tests. You don't need to do anything crazy. So that's that. Now we have the conclusion. Okay, so the original series is also divergent by basic comparison. Okay. Again, very intuitive stuff. We're just writing it down. We are giving the argument a structure. We are writing it down so that we are convincing.
Professor, how are-
I'm sorry. I'll have you talk in a second. The book doesn't want you to. They don't require you to show steps. There are no steps. Okay, they just pick a. They pick a b sub n. They say, hey, it's more or less, and then they say what happens. I need you guys to give me all the 4 steps on the test. Okay. Yes, Ahmed.
yeah, I was gonna ask, so yeah, so for the last example, we got that a sub n, like it converges. So how would we find like the sum of the series then?
We can't. We can't.
Because that got, yeah, because I was thinking, I was like, how are we supposed to find the sum of that?
Guys, remember what I said? Ahmed, remember what I said? With these questions, with series questions, the goal is to say if it converges or diverges.
Okay,
That's it. No one is asking us to find the sum. How are you gonna find the sum? I don't know. Ask me. Ask me how. I don't know. That would be my answer. How do you find the sum? I have no idea. I don't care.
okay.
Yeah.
So you can only find it for like geometric series, right?
Yes. If you have a telescoping series, if you have a geometric series, you can find the sum for those. Okay.
Okay.
But the questions here, the question is, does the series converge or diverge? That's all. They're not asking what it converges to, or yeah, if it's convergent, what it converges to. We don't care. We just want to know if it's convergent or divergent.
Oh, okay. Yeah, that clears a lot of things up because I was like, wait, I don't know how to find the sum of that. Like it looks kind of impossible.
Yeah, but what about, I mean, I didn't even find the sum. We can't even find the sum of this. We can't.
Right. Okay.
Yeah. We just want to know if the series is divergent or convergent. That's it.
Okay.
Okay. So guys, when you come back next time, we'll do a question with factorial in it. I want you to go over factorials before Monday. When you come back on Monday, please know about factorials. So just look it up. If you probably haven't studied factorials in the past, I want you to look up factorials. Okay, so look at the definition of n factorial. What does n factorial mean? It's just n times n minus 1 times n minus 2 and so on. For example, 5 factorials, 5 times 4 times 3 times 2 times 1. You stop at 1. Yes, you got it. So try to remember this, okay? Try to look it up and study a little bit, study the details of it a little bit if you can. Like how you can rewrite factorials, what can you do with them algebraically? All right, and I'll see you on Monday.
Thank you.
Thank you, Professor.
But Jose,
Thank you.
you're welcome. For how many values of P do we know the P series? Oh, I guess Jose, you can find a value of the series for any P more than one. Not integer powers of P, like one, no, not one, but 2, 3, 4, 5, 6. You can find the value of the series. There's a way.
And also, Professor, so these, how do I say this? So these examples for like basic comparison tests, like, does it only apply to like rational examples or no? Like, so far we've been doing like
Fractions.
fractions, yeah, which is much.
No, and no, it does. It could apply to any type of series. Yeah.
Okay. All right.
Yeah. For example, like n 2 to the negative n, which is actually a fraction.
Yeah.
It's a fraction, or so if it's not a fraction, then the sequence is not decreasing. So it has to be a fraction. Like every sum you're dealing with, every series you deal with, has got some sort of a fraction involved. Because if it doesn't, then the series is going to blow up. You know what I mean? We have to have a fraction, because if we don't have a fraction as our sequence, then the terms are not going to get smaller and smaller. So by nth term test, it's just going to diverge. Does that make sense? What I'm saying?
I'm a little lost. Like,
So, okay, so give me an example of not fraction.
Okay, like let's just come up with like a random addition series.
Guys, you have a great weekend too. Yeah, tell me.
How about like we come up with like a random like
You
addition?
come up with something.
Okay, so we had like, so we have 1 over square root of n minus 1. Let's just do like square root of n minus 1 as our ace of n.
I got you, but you see, this is not interesting at all. You know why, right? Why would this not be interesting at all?
I mean, you can't really apply the P theorem here because it's not in the form.
So hold on, what was Raya's asking? For the P series test, does it work even if the series doesn't start it? Yes, Raya, yes. It could start at anything. Yeah. So yeah, you were telling Ahmed, why isn't this not interesting?
Is it again because it's not decreasing, like how you?
Right. I mean, the nth term test right away says that this is divergent, because when you take the limit of root n minus 1, you get infinity. Right? This is not the series doesn't require any investigation. Right? So if n starts at 1, first term 0, second term is root 2 minus 1, third term is square root 3 minus 1, then you have root 4 minus 1.
Okay.
Right? This thing just keeps getting big and bigger. And you're just doing minus 1. So this part goes to infinity. Infinity minus 1 is infinity.
Okay.
But you're adding a bunch of terms that keep getting bigger and bigger. So the series is obviously divergent.
Okay.
Right. So that's what I was saying. Typically, if you don't have a fraction, if the sequence is not in some sort of a fraction form, then the sequence is just going to keep getting bigger.
Yeah. Yeah, that makes sense now that I think about it, because you're just adding terms forever.
Yeah.
Okay.
So something else like that would not be in fraction form would be like, say, n e to the negative n. But again, this
can rewrite it.
Yeah, power is negative, so you can write that as n over e to the n. That's still a fraction. Yeah, if it's not a fraction, then it's not gonna go to 0. So you'll get divergence right away.
All right, cool. Thank you. Oh, and you have office hours today at 9:45.